Assalamualaikum and very good morning. How are you guys? This is our last topic, which is chapter 12. I really hope that you are still with me, okay? And wherever you are, please stay safe, okay? And keep on a set point tracking and disturbance rejection. Okay, so this chapter is about PID controller design. Last time during chapter 8, during chapter 8, you have learned about PID controller. You have been introduced about what is proportional, what is integral, and what is derivative, the function, the definition of these three modes, and you also been introduced to the response, okay, the response of this controller, okay. So here in chapter 12, we're going to see the design of this controller. Okay, what does it mean by design? It's basically involve two things. The first one is to determine, okay, to determine our GC, it be P, PI or PID. We need to determine our GC to be P, PI or PID based on the model. Okay, later on you see in detail based on the model, which is this model, it is from GP, GM and GV. Okay, and the next one is for you to determine what is the value of Kc, the value of tau I, the value of tau D. Okay, this is two things that really important for the real case, the real definition of design the controller here. Okay. And this topic, chapter 12, okay, there are three major components in this topic. The first one is for you to design, okay, for you to design. The second one is you just use a tuning relation. And the third one is a online tuning. We're going to revisit about online tuning, okay, although you might have you already know what is online tuning, basically lab number 8 and your lab number 8 doing that's online tuning together with your pH and temperature. So I will try to answer all the questions about online tuning here. Okay. To start with, remember this our standard block diagram of feedback control system. Okay. So in chapter 11, okay, versus chapter 12 here, okay, in chapter 11, the value of GC, okay, the transfer function for controller, which is GC, already been decided whether it is P, whether it is PID. Okay, based on the example of liquid level control system, there are cases for P controller and PI controller. So the GC, the transfer function of GC is already decided to be whether P or PI. As compared to this chapter, which is chapter 12, actually we want to determine what is GC. Okay, in this chapter, chapter 12, we want to determine what is GC based on GV, GP, GM, or also GD. Okay, so that is the difference. I really hope that you can differentiate between chapter 11 and chapter 12 and don't get confused. Okay. Okay. So this is a performance criteria, meaning to say the performance of the closed loop, the response of the closed loop should be, okay, the performance of the response is based on the controller. A good controller will give you a good response. Okay? A bad controller will give you unstable response. Maybe it might give you a overdamp response, or might be giving you a delay response and whatnot. Okay, so the first one, why we need to design our GC, okay? Because remember our closed loop transfer function, okay, or our closed loop system, okay, our closed loop system, the response from this closed loop system should be stable. Okay, it should be a stable response. Okay, how to know whether it is stable or not? We will see an example later on. Okay. And then a good controller also, number 2, it will uh, provide a good disturbance rejection. A good controller should have a good disturbance rejection, meaning to say the controller can bring back the system into the set point. Bring back after the disturbance occur, uh, the response, the controller can still bring back the system into our desired set point. Okay. And number 3 is a rapid and smooth response to set point change. Okay. A good controller also a good set point tracking, meaning to say when we change a set point, when we introduce any set point, the controller can bring back the system into that set point. Okay, if we can see from a graph, okay, this is a graph for step input. A good controller can bring back the process, bring back to the set point. Regardless, you change, you increase or you decrease, the response can bring back to the set point. Same goes with disturbance rejection. Okay? When you have disturbance rejection, the controller at a steady state and the system at a steady state and some disturbance occur, so the response is controller can bring back the response back to the steady state. So meaning to say it can reject the disturbance. Okay? And the fourth one is the offset. Offset is eliminated. Okay? As you all know, offset occur when you have P controller. Okay? And it doesn't mean that P controller is not always not good, but there are cases that P controller is enough, although it have an offset. Later on we see. Okay, and then the fifth one is excessive counter-action is avoided, meaning to say the controller uh, do a corrective action appropriately, not excessive. Okay, I will find an example to explain this one. Okay, the last one, the control system is robust. The controller should be robust. What does it mean by robust? Robust that can operate at wide range of operating condition. Okay? It is unsensitive to the changing of process condition or to inaccuracy of the model. This is really process control. Okay, and about robustness is chapter 15 or 16. It's not in your syllabus, but for your understanding, it is enough for you to understand that robustness meaning to say that this good performance of the controller should be in a wide range. Okay, this is good set point tracking, set point tracking, and good disturbance rejection. Okay, good set point tracking and good disturbance rejection. This one compared to only this one. The good thing only here compared to the good thing within this operating condition. So this one is robust. Okay, a good thing at a wide operating condition. Okay, I know it might sound confusing, but don't worry, this is a theory. But in a simple word, say that a good controller should have a good disturbance rejection and a good set point tracking. Okay? I do believe that when I say disturbance rejection, you can understand what does it mean by disturbance rejection, whereby it can reject any disturbance and bring back to the set point. For example, in our life, due to this pandemic COVID-19, it is a disturbance in our life. So can we reject this disturbance? Okay, later on we see the example. What does it mean by this? Okay, this is an example, okay, of response. There's a lot of response here. Can you determine which one is the best response? Remember, a good controller will produce a good response. In order for us to evaluate the performance of the controller, we can evaluate from the response. Okay, from a response you have learned you have learned and you already calculate the settling time, the rise time, the overshoot, right? The period of oscillation and whatnot. Okay, so here, in order to determine whether this response is a good response or not, you have to calculate all these three values. You have to compare, okay? You have to compare between all these response, which one having the shortest settling time, which one having the highest overshoot, or which one is a overdamp or underdamp response. Okay, let's see. Okay, what we have here is the different value of Kc. Okay, when you have Kc equal to 1, you get this response. Okay, when you have Kc equal to 1, you have this response. When you have Kc equal to 3, this is the response. And when you have higher Kc, this is the response, together with the difference of tau I value. Okay, for this one, this is called unstable response because the amplitude of oscillation is getting bigger and bigger. So this response, it is unstable response. Okay, this is what we don't want. We don't want it. Okay, we don't want this kind of response. Okay, because we want a stable response. A stable response means opposite from this one. Okay, whereby it can settle down to a steady state. It can reach a steady state. Okay, that is a response that we want. Okay, so in terms of settling time, let's see the settling time for all this response except this one, because this response, this system will never reach steady state and there is no settling time for this because it's never settled. Okay, just calculate the settling time for each of these response. Okay, so for example here, okay, about here the settling time, okay, here maybe around here also, okay, and this one maybe around here, okay, and this one could be here, this one, okay, you might need another line here so that your response be somewhere here, Compared to here, it could be somewhere also here. This one also about here. And this is a overdamp response. It could be somewhere here. Okay, from the settling time, can you determine which one having the shortest settling time? Okay. For controller number 1, it is unstable response. But for the controller number 5, it is the best response. Okay, I'm giving you the answer. This is the best response because it has the shortest settling time. Okay, can we compare in terms of overshoot? Okay, in terms of overshoot, which one is higher compared to this one, just about the same. Compared to this one, it's a lower. Okay, it's a lower overshoot. But compared to the bottom one, it is a higher overshoot. Okay? And then the rush time is difficult to see here. Okay, because we need another maybe we don't need rush time here. Just enough when we have a settling time and oscillation. Okay? So do you agree that this controller number 5 is the best response because it has the shortest settling time together with it has the least oscillation. Okay? So in general, when Kc is increased, okay, or tau I is decreased, the response is more aggressive. Aggressive means more oscillation. Okay, more oscillation. Okay, so this is the summary. The main component of chapter 12. Okay, the first one is the PID controller design. There are two methods, but we will just cover this first method. The second method will not go into detail because we will see the detail here. It's same, IMC, and also here is IMC. So we will see the detail here. Okay, and then another tuning relation here is a lot of tuning relation here that we just use. Okay, and then our online tuning. Okay, remember what is PID tuning? What is tuning? Okay, tuning is to find the best value of the best. Okay, the best value of Kc, tau I, tau D based on that particular system. That value might not be the same, okay, but it's really specific for the specific case. Okay, that is a tuning, meaning to say to find the best value of Kc, tau I, and tau D. Okay, let us start our PID controller design for method A, the first method, which is a direct synthesis method. Okay, so remember our closed loop transfer function for set point change. Okay, I hope that you're already familiar with this. Okay, from this you have to simplify, whereby you substitute you substitute GP, GV, and GM. We make it as a G, and GM is still equal to KM. So we substitute this one into G, and the G do it for set do it for both numerator and denominator. Okay, and then we make we put GC, we rearrange so that GC will be our perkara rumus. Okay, so you get this one. Do you have any problem to do this? Just rearrange. Okay, and then the next step is to substitute the y over y as p, put it a letter d. Why we have to put it as a d? Because d is our desired closed loop response. Desired meaning that what we want. Okay? If we have y over y as p only, it is a general form. Okay, it is a general form, but to specify it to become the closed loop that we want, we put d. Don't think too much, just put d there. Okay, and then for the first case is the desired closed loop transfer function is this one, which is a first order without time delay. And substitute this into this, you will get this. Okay, so let us derive this, okay, from a closed loop transfer function for set point change. Here we simplify, we put g equal to gv, gp and gm, so our km is still equal to gm. Okay, and then we simplify, so our closed loop transfer function would be GCG together with 1 plus GCG. Okay, so and then we multiply, crossover. Okay, so we have y over y sp, put it together. Okay, plus y over y sp GCG equal to GCG. Okay, okay, and then we put GC minus y over y sp GCG equal to only y over y sp. Okay, before that, one thing that I forgot, remember that when we have y over y sp desired, so we just put d here and d here, here and here. Okay, so this is only g, sorry, this is only g. Okay, so we factorize g. Okay, g minus y over y sp, okay, g equal to y over y sp d. Okay, so we make our gc as our vector. Okay, so gc is equal to 1 over 1 y over y sp d over, we factorize g. Okay, so we have 1 minus y over y sp d. Okay, is it correct? Okay, so we get this one. So we get this equation. Okay, so we continue. Okay, when we get this equation, the y over yp Okay, when we get this equation, okay, when we get this equation, we will substitute the value of y over y as p. Okay, there are two cases. Okay, the first one is first order without time delay. Okay, first order transfer function without time delay. And the second one is a first order with time delay. That's one. Okay, so let's take it out our slide. Okay, so when we get this equation, we will substitute the y over y as PD. This is our first case, which is a process without time delay. Okay, this one, and you should get this one. Try to substitute it. And the number two, okay, case number two is a process with time delay, which is this one. Okay, so this is a symbol, this is the equation that represents time delay. Okay, and exponent negative theta s approximately equal to 1 minus theta s. And you should get this. Okay, let us continue our derivation. Okay, so let's see for the first case. Okay, for the first case, okay, when we have this one. Okay, so when we have that, okay, we just copy back. DC is equal to 1 over tau CS plus 1 over 1 A over 1 minus 1 over tau S plus 1. Okay, don't get yourself confused with the line. Okay, make sure you arrange it properly. Okay, so when you have this, what you need to do is you have to time everything should be timed with tau CS plus 1, then goes with the denominator. Okay, so the top one we left only 1 over, okay, G, just put it as a G, and this one, this term times this term, okay, this term times this term will be tau CS plus 1 minus 1. Okay, so that's why you get 1 over G and divided by tau CS. Okay, so the GC. That's why you should get this equation. Okay, put it like this. Put it like that. Okay. We put it as a different term. Put it as 1 over G, 1 over tau CS. Okay. And there are a symbol of G here, meaning the G is a model. Okay. This one is a real G, and we make it as a model because we never known a real model for, because we have only mathematic model that is called model. We don't know the real, we don't have the information about a real equation. We can just predict whether it is first order or second order. Okay, So same goes when you have case number 2. Okay, let's derive for case number 2. Okay, same method. Okay, same method. Okay, the same method whereby you substitute G equal to K exponent theta S over tau CS plus 1. Okay, sorry that I have to go back to this slide because I don't remember. Okay, there is no K because K is equal to 1 here. Okay, so there is no K. So you just remove it. Remove this one. Okay, don't get confused. Okay, don't get confused. It's just the K value. Okay, so you substitute the same. Okay, over 1 minus exponential negative theta S over tau CS plus 1. Okay, and don't forget your G outside. Okay, so to do the simplification, time everything with 1. Tau CS plus 1, tau CS plus 1. Okay, so your GC would be on the negative theta S over tau C, over, sometimes it's really hard to erase it, I don't know why. Okay, so you have also here G model. Okay, so here you have tau C S plus 1 minus exponent negative theta S. Okay, so you continue here. Okay, your GC is equal to exponent negative theta S over your model. So in a bracket, you will have tau S plus 1. Remember that exponent negative theta S is equal to 1 minus theta S. So you just put it as plus 1. Okay, we have exponent negative theta S over G in a bracket plus 1. Okay, plus 1 minus in a bracket 1 minus theta S. Okay, because this term is equal to this. Okay, and so we have GC is equal to exponent negative theta S over G model tau E. Oh, I forgot my S. 1 minus 1 plus theta S. Okay, so your final GC is equal to exponent negative theta S over G model theta C tau C plus theta S. Okay, so I hope that you try yourself because it is I think it is included in your CA. Okay, so make sure you try to derive this because we will continue further. Okay, the next step is when we have this GC, when we have the model, okay, we divide it into whether first order plus time delay or second order plus time delay. Okay, so the model, the process model will be divided. There are two cases. Okay, first order plus time delay and second order plus time delay. Okay, when you have a first order plus time delay, okay, first order plus time delay, okay, it is, okay, G is equal to K exponent negative theta S over tau S plus 1. Okay, so we're going to substitute this into this. Okay, let's continue. When you substitute that, your GC is equal to negative theta S exponent negative theta S over, okay, over exponent negative theta divided by, don't forget your K, tau S plus 1, and in a bracket tau C plus theta S. Okay, so to continue, okay, we can cancel out, okay, we can cancel out this term and this term, okay, so that it will be something like this, 1 over K tau C plus theta S over tau S plus 1. Okay, and then you should get tau S plus 1 over K tau plus, K over tau C plus theta S. Okay, make sure you try by yourself. Okay, don't get confused. So you will get, you have to simplify further. Okay, tau S over K tau C plus theta S as 1 over same numerator, same denominator. Okay, tau C plus theta S. Okay, simplified, cancel this one, so it will be tau over K, sorry, not in this color. Okay, so it would be tau over K tau C plus theta plus 1 over K tau C plus theta S. Okay, there is S there. Okay, when you get this, okay, when you get this equation, okay, your GC, it is GC, don't forget your GC. Okay, you have to compare with a standard transfer function of controller, which is GC equal to KC 1 plus 1 over tau IS plus tau DS. Okay, you have to compare with this one. Okay, in order to compare, okay, the first thing that you have to see is, it is here 1 plus. So here you have to factorize. Okay, you have to factorize. Okay, you have to factorize in order to compare with this one. Okay, compare with this one, you have to factorize, put it as GC equal to tau over k tau c plus theta 1 plus. Okay, we factorize this, print out. Okay, factorize over. Okay, this is quite crucial. Okay, when we factorize this, okay, this one, what should we time here so that we get this one? So it is this is mathematics. Okay, don't get yourself confused. Okay, it is a mathematics factorize. Okay, so it is only 1 over tau s. How do I know this is tau? Remember that when the easiest way to check is if you pen it back, if you time with this one, you should get this one back. So this is a factorized operation, mathematics form 3. Okay. So, and from here, why we have to compare? The question is why we have to compare with this standard form? Because we want to determine what type of controller here. What is GC here? It is P or PI? It is PI. Why PI? Because it has only 1 and 2 terms. Right? 1, 2. P, I, and D. P and I. Okay? So the controller here is PI controller. Do you know how to calculate KC? This is equal to KC. This would be equal to tau I. So you will get KC equal to tau over A tau C plus theta. And your tau I is equal to tau. Okay. So this is the derivation on how to design a controller when you have first order transfer function of a process model. Okay. So our G here, we call it as a process model. Okay. It came from GV, GV, and GM. Okay, so our process model, okay, when we have process model first order, we will get PI controller. Why PI controller? There's only P and I. Okay, this is a standard form of PID controller. You should memorize this. You should know. Okay, I'm sorry that it's quite messy around here, but you have to try. Okay, so please watch this derivation many times. So try to derive by yourself because I want you to derive for second order. Okay, when you derive for second order, did you manage to get a PID controller? Okay, so this derivation, I don't remember whether it is a first order or second order that will be one of your CA. Okay. So let's go back to our slide. Okay. So in this slide, when we have first order plus time delay, which is this one, we substitute into this and compare with the standard form of PID controller. You should get PI controller. With this is the equation to find the value of KC. this one to find the value of tau I. Okay, remember a controller design for us to determine what type of controller. So here we have PI controller, and then for us to determine the equation to calculate the Kc and tau I. Okay, that is a controller design. Okay, when we have a second order plus time delay, there's a typo here. Okay, it's a typo here. Okay, when we have second order, repeat the same step, substitute into this one, you should be able to get PID controller with Kc equal to this, tau I equal to this, and tau D equal to this. Okay, try it first. If you have any problem, please let me know. Okay. So this is all about direct synthesis method, which is one of the methods to design a PID controller. The next one is an internal model control, whereby we're not going into detail about how to derive it, because we take a look about it on part 2. Okay, so I will just go fast with this. Okay. Internal model based control, it have another model here. Okay, this is really process control that I don't like to talk about too much. Okay, and then this is how to derive. Don't worry, you don't have to derive this. Okay, and we will just straight away go to component 2.